and French fries. They have a shrimp Alfredo, make Cajun.
Sí.
Okay, good evening, everybody. We'll get started in just a second. So give me just a couple of minutes. See if we get anyone else who's going to join us. It's going to be a little short tonight. I'm going to do a quick demo of Ltspice for those of you who haven't done it yet, and entertain any questions from there, and we'll go from there. I apologize for not getting the reading material to you last night. Had some little technical difficulties, but I will send it out tonight. So give me a second. Okay, I have returned. Thank you for your patience. Tonight should be fairly short. What I'm going to do, 1 second here. Yeah, you can show me. So for those who haven't used Ltspice before, you can download it fairly easily. Just do a Google search on Ltspice, but it's on the analog devices webpage, so you can get it from a lot of other places also. It runs on Windows and it also runs on the Apple products. So let me start here. I've already downloaded it, and let me start sharing my screen. Let me know if you have any questions. Let's see, share screen. Okay, 1 second here. Doesn't like the way that window looks. So let me stop sharing for a second. Make the window larger. There we go. And now share screen. Not sure what's going on. Let me see. Oh, here we go. Everyone see me moving around this screen that has this funky brown background on it?
Yes, sir.
Okay, thank you. All right, so I just brought up Ltspice. LT stands for Linear Technology. It was a standalone company until it was acquired, I don't know, about 3 years or so ago, maybe a little longer, from by another big analog and power company called Analog Devices out of Massachusetts. So when you bring up Ltspice, I think, yeah, this is the latest version. This is my latest version, but there's an update which I haven't run yet. So here's what the screen looks like when you first open it up. Let me scroll this across so we can see even more stuff. And we'll talk about some of these icons here, which are not that necessarily hard to figure out. But what I'm going to do is I'm going to build a schematic for the circuit that we analyzed last night in class, and then run the simulation for it. We're going to run operating point, so we can take a look at your base current, collector current, emitter current, base voltage, collector voltage, emitter voltage, and then run the transient or time domain simulation for it, so you can actually see what the gain looks like. And from there, we can do all kind of cool stuff. So here we're going to do, this opens a file. We're going to do a new one, new schematic. Okay. And then I'm going to talk about some of these as we go across the top here. This pencil here allows us to draw wires to hook things up. This labels a net. We'll get back to those later. But as we get across here, here are your components. Here are your resistors, your capacitors, inductors, diodes, and this says components, which includes a whole bunch of stuff. So let's hit components. And what I want to do, I want to use a specific transistor, but I can't, be honest with you, I can't figure out exactly where it is. I want to use the 2N3904 transistor. But what I do know is I want to use an NPN transistor. So I'm going to click on NPN, and it'll just give me a generic device. And you just left click and drop it. So now, what I'm doing here with my mouse wheel is I'm scrolling, which zooms in and out. So next, let's build the rest of the schematic. We're going to put some resistors down. So I click here, I click, and the resistor sticks to it. So I'm going to put one here in the emitter, one here in the collector. And then we remember the R1 and R2 we have for biasing. Put those over here. Make sure they line up. Escape to stop. And now I'm going to wire them up. Click my pencil here. Click on one node, click on the second node, and draws a wire between the two. So those are electrically connected. And we do the same for the rest of these. Up here, we're going to connect our supply VCC. We haven't put it down yet. And down here at the bottom, we're going to collect our ground symbol, which every circuit needs to run properly, but we'll get that also. And now I'll connect my base to this junction here for our bias. So let's see, we need a ground symbol. So I'm going to come over here, component. Well, there's another place to get it. Oh, there it is. Let me close this for a second. Here it is up here right next to my wire symbol is ground. So I just collect that one, drop it in here. I'm going to put another one over here, and you'll see why in a minute. Oops. Forgive me for this scrolling. And then we're going to come back over and get another component. And we need a power supply. Let's see, that should be under V for voltage. And this is what it looks like. Now, this power supply can be used for DC, AC, transient, pulse width modulated. We go into a little window, or excuse me, a little template, and we change the parameters we're interested in. So, okay. I'm going to put this, and we'll put it here. I'm going to move my ground. This hand symbol here allows us to move things. So I'll collect here, slide over and drop it. Back to my pencil to connect my supply to ground. And you select this ground here on the bottom to the bottom of my transistor circuit. So these grounds are the same point. And I did like this specifically. Sometimes it helps to keep your drawing from being messy. You can actually separate things and then connect them with common symbols like this, or we can connect this by drawing a wire over to here and then labeling this VCC, or we could, well, we'll do that another time. Let's just keep it simple for now. So here's our circuit. Right now we don't have an input, but that's okay. We're just looking at the operating point. Now, if I remember, so if we come here and we left click on this resistor R3, I want to call it not R3, I want to call it, I always call mine R1 at the bottom. And click OK, and it changes the name of it. If I click on the value right here, R, I can change it. And I believe from last night, this was 11K. So we type in 11K for 11 kilo ohms. And we've changed the value of it. And up here, we're going to make this an R2. And if I remember correctly, its value is 51K. So it's R1, R2. Now here, this guy, we would actually call RE. But actually, we selected the resistance instead. So let me get to just the R. Here we go. We will call this RE for emitter. And now let's change the value of it. I think this is 1.5K. And then this is RC, our collector resistor. And its value, if I remember correctly, was 4.7K. And there's our circuit. Almost done, but not quite. This supply voltage is V1 here. We're going to, I'm right clicking on it with my mouse, and I'm going to set the value to 15 volts. Click OK. So that's the name of it is V1, its value is 15 volts. This node right here is VCC. So I can come up here to the label net, this thing labeled A, left click on that, And I'm going to call this node VCC. Okay. And then drop it on here. So now this entire net here is called VCC. Let's hit. I'm also going to name the rest of these. I'm going to name this node here VC, this one VB, and this one VE. So here, VC. And then I want to name, maybe, nah, I don't like that. Maybe a way of doing it easier than keep going back to it, but I don't remember how to do it yet. But we can do, oh, this is undo right here. So I put this down, I didn't want it. I can just do undo. If I decided I actually did want it, I can do a redo. Okay. So let's continue to label these. I'll do VB on this node. And then the other is BE. It goes right there. So now I have all of my nodes labeled. This is VCC. This is VB. This is VC, and this is VE. I want to try to do something. It may not be in this version where I can highlight all the nets. Let's see if it's here. Yeah, here we go. So if I want to know what all connected to these transistors, I right click. Yeah, right click on this node here. Oh, excuse me. The other right click. And hit highlight net, and it shows all of the nets that's VCC. Escape to get off of there. I want to see what's all on VB. Right click, highlight net. All of this is connected together. If you don't have some of these connected, then that node will just be floating and have some funky name to it. What I did was I named each one of these nets. So when this thing simulator runs, I'll know exactly what VB is. If I don't give it a name and I want to know what the name of the base voltage is, the simulator would just give it some random name, but I won't know exactly what it is without looking for it. So it's a good practice to label all of your nets like this. Now
Sir, can you show, so just to make sure, so how you was able to put
hold on one second.
VB there?
I'm sorry, say again now.
So how you was able to put the VB there was you right clicked on that line, click label net, then typed in VB, correct?
Yep, I can do it that way. I right click on it, or I could come up here and hit label net, type it and drop it here. Either way. So you got a couple of different ways you can do it.
Okay.
Okay, so now we have everything that was hooked up last night, and we did our little calculation and we ran our simulation. Excuse me, did our hand calculation to determine what your collector voltage, base voltage, emitter voltage, the current emitter and collector current were. So now let's run the simulation. So we come up here. You can hit use this label called simulate, or you can click on the running man, which is run. So let's do simulate. Actually what we need is, oh, I need to tell it what I want to run. Well, I wasn't planning on going here, but since we're here, let me talk about this very quickly. So I hit simulating control panel. You can control the accuracy at which the simulator runs. So here you get an absolute current accuracy of one, what is it? 1 nano amp of accuracy. And here a voltage, absolute voltage accuracy of 0.1 microvolts. No, excuse me, 10 microvolts. And then a relative tolerance of 2.5 millivolts. So if you wanted the numbers to be even more accurate, you can change these. These are the default values, and they usually work fairly well. But if under some conditions you need to be more accurate, you can change it. Or if you find that you don't need as much accuracy, if you make these tolerances looser, your circuit will actually run faster. Okay, so let's do a cancel here. So we click here, the running man, and we choose our analysis. Well, we don't have an input source yet, so what we're going to choose, we want to look at DC operating point here to the far right, so we click on that, and that window pops up. And that is it. So it says compute, it tells you what this option does. Compute the DC operating point, treating capacitances as open circuits and inductances as short circuits. And what will show up on our schematic is this command here, .op, which means run operating point. Basically calculate all your DC stuff. So we hit plus here. It shows it here, and then we run the simulation, and here's the data. So let me slide over here a little bit. Over here, you see, and here's one thing I liked about Ltspice that was a little weird for me coming from the Cadence tools. The Cadence tools, you actually had another window or a file where you set up your simulation commands. Ltspice puts your simulation commands right on the schematic itself. So there's not another file you need to go to set up. You just click it through the menu. So here's our operating point. I'm sorry, go ahead.
So when you click run it in that file came up, what were we supposed to type in for, like, run times, time to start, save data and stuff? Like, what do we do for that? Or do we do DC or AC?
Hello. So we're here. We do this.
Yeah.
I had set up simulation to only do operating point. So you don't have to worry about runtime. Operating point, nothing's moving. Because we don't even have an input signal yet.
Okay. Just run operating point. Okay, I got it.
Choose that window that says operating point. We're going to get to the transient one in a second when we add our input signal here. And then we're going to look at the output. But we'll get to that in just a second. Okay, so here's our operating point. It says that first of all, it says my VB is 2.56 volts. And I think we had hand calculated, what was that, 11 over 62 times 15, 2.66 or something like that. So that's pretty close to what the hand calculation value was. Then we got 2.55 for VB. Subtract about 0.7, and we get VE of 1.77 volts. Which seems a little big. Now, understand too that this is some generic transistor. I have no idea what the model parameters of it is. But now that we have got this in, we've run an operating point. We got some numbers, and the numbers make sense. I mean, the numbers are reasonable. Here's my collector current, which is 1.17 milliamp. My base current is 11.7 microamps, which gives me a beta, if I take IC over IB, of about 100. IE is approximately equal to IC, except it's negative. IC is going into this node. IE is coming out of it. That's why it has a negative sign. And then it talks about the current that's flowing through resistor R1 and R2. The current through RC, which is IE, which is also IC, which is 11.7. I'm sorry, not 11.7, 1.17 milliamp. And then the total current coming from this power supply is sum of all these currents here, which is about 1.4 milliamp.
Sir, I'm having my values are a little different from yours. I don't know what I'm doing wrong.
When you say different, how different?
Like very, so say for example my VC I got like 0.88.
I would probably guess that you have something not connected properly. Let me point out a couple of things on the schematic here that I've drawn. So I know these numbers about right because one, I did the hand calculation. And so I expect to get something similar to what I calculated in class. But also, I'm looking at my schematic here. Let's see. I know that these two should be connected to the same node. That's why I did a right click. Oops, I can close this for a second. Right click here, highlight net. All of this should be connected to the supply voltage. I would suggest you try that with yours also to make sure everything here is connected. If I come down
Yeah.
to VB, highlight net, all of these should be connected.
Yeah.
Escape. Let's look at VC. Highlight. This resistor should be connected to the collector of your transistor.
Said VC. Yes.
And then the other is right here, VE. That should connect the emitter to this emitter resistor.
Mm-hmm.
And then here at the bottom, these two resistors should be connected to ground, which also connects to this guy over here.
Yeah.
Okay. Now the other thing to look at is your values. Do you have 4.7K or do you have something else? The K matters.
I have I think it's an uppercase K I have right there.
Okay, that should be okay.
And I do have 51K for R2, and R1 I have 11K, and then I have for RE 1.5K.
What device do you have here? Is it an NPN?
It's a NPN.
Is the arrow here connected to your emitter?
I believe so, but I can check.
Well, you just have to look at it to tell.
Yeah, it is.
Okay. I'm not sure what you're missing then. Do you have your supply voltage here set to 15 volts?
But I have 15V right there. Does the V matter?
Get rid of the V.
Okay.
It thinks the V is actually a prefix, like K, meg, micro.
Mm-hmm.
Yeah, you don't have to put the units here because the units are over here. I bet if you get rid of the V, that will probably take care of your problem.
Okay. Okay. Let me run. Now it's like, say for example, my VC is 0.083 volts or whatever.
Uh-huh.
So yeah.
It should be 0.083. It should be more like 8 point something or 9 volts. So let me run mine again. Let's see, VC here should be 9.48 volts.
There it goes.
Okay. So that V was the problem.
Uh-huh.
Yeah, it thinks that the V is some some suffix, like an M after 10 will give you 10 milli. It thinks the V is I don't know what V is, but it got confused. So that gives us our operating point. Now let's see if I can do this. This was a generic NPN transistor. I don't want that one. So I'm gonna right click on the transistor and it says right here, it says pick a new transistor. So I'm gonna click pick and it takes me here and we can choose a 2N 2022 or a 2N 3904. I'm gonna choose the 3904 and go okay. So now let's change this to this particular transistor with this particular transistor model. So there's a model file for this particular transistor that's different than that just generic one that I just pulled out of the library a minute ago. And so now let's rerun. And lo and behold, we get different numbers now. We have 8.86 before, for now for VCC for VC before we had 9 something. Where's VB? Here you go. VB is 2.62. It was like 2.77 or something before. VE is 1.96, which is pretty close to what we calculated last night. And then here's IE, 1.3 milliamp. And we didn't calculate the base base current, because when we're doing a voltage divider bias here, we never need to figure out what the base current is. We just need to figure out what this voltage is, and then do, subtract 0.7 to get VE, and then divide that by this resistor to get the current here. And then we could take that and divide it by beta to get IB. But this particular configuration is called beta independent. If I took this transistor and put another transistor in with a beta of, say, 80 as opposed to 100, there shouldn't be much change in my current that's calculated or in my collector emitter voltage. So, but these resistors here have to be a certain value with respect to this resistor here. So let's see. So let's see how much current actually flows. So R1 is the current that's flowing through, excuse me. The current that's flowing through R2 is here, 0.238. I'm sorry, looking wrong one. R1 is basically it's 242 microamps. That doesn't sound right. And the current that goes to R1 is a little less. And the reason it's a little less is this current comes here. Most of it goes here, but some of the base current goes here. So this is not going to be exact. The voltage divider bias methodology assumes that 0 current flows into the base, which we know is not true. So you're going to get about a 1 or 2% error in your numbers, but that's actually acceptable. So this is how you build your schematic, and this is how you run your operating point. And now we can look at this and it's like, well, yeah, the base voltage is about 0.7 or so higher than the emitter voltage, so that's okay. We also should look at whether or not the collector voltage is greater than the base voltage. The collector voltage is 8.86. The base voltage is 2.62. So this transistor is actually in the correct region of operation. It's been a while since I taught electronics 1, and I don't know if they teach actually checking to make sure that your transistors in the correct region of operation by checking your voltages here. So we talk about the base being greater than the emitter if this is actually on and current is flowing. So this minus 0.7 gives me VE. The other thing is that the base voltage here can't be more than 0.7 volts higher than VC. So this can get higher, but it can't be more than 0.7 volts higher than VC, because actually in here is another diode junction, which we don't show explicit like this. If VB gets too much higher than VC, current actually flows in this direction. And then the transistor doesn't operate the way we've been assuming that it does, because it's in a different region of operation now. But when you're running something like this, a quick check is the base voltage like 0.7 volts higher than the emitter voltage? The answer is yeah, okay, we know it's on. And is the base voltage less than the collector voltage? The answer is yes. Then we're probably biased up okay. So that is doing the operating point part of what we did by hand last night. Now let's draw the rest of the circuit. See, what do we have? We had a capacitor here and a resistor to ground. So we had, I want another resistor. I can go up here and select another resistor, but what I really want is another resistor, this same value here. So I can do a copy right here. These two little sheets is a copy, and do a left click on it, and it copies that value, but it changes its name slightly. So we're going to drop it, see about here. And what else we need? We need a capacitor. See, the capacitor is here. So select that, it brings it down. I want to rotate this, so I do a Control R, and it rotates it. And I want to drop it here so it connects to your selector. Now we're going to need another capacitor also on the input over here. So I'm going to go ahead and drop this here now. And I'll get back to it in a second. Let me wire this up to the output. This was my load resistor RL, so I'm going to change the name to RL. And say OK. We have a new node here that we didn't have before. So we can right click on this, label net, and we're going to call this V out, this VO. And OK. And then over here we also need another voltage supply. So we have one here. So let's just copy it and we'll modify it. So we'll copy here. Drop this down here. This guy also had what was it? Like 1.1 well, 1.1 ohm of source resistance. Which, hold on, let's see something. So we can do this two ways. We can close this one. We can explicitly put our 1.1K resistor in the schematic, just like it's drawn. But you can also, if you right click here, you can put a series resistance directly on the supply. So it's actually part of this model here. But we're going to do it explicitly so we can see it. So let's see, I take a resistor. Let's do we'll just grab another resistor in here. And do a Control R, rotate it. I want it to look like this. Then I want to move my, up here. My voltage source over here. And now let's wire things up. So this capacitor here went to the base. And then we have this capacitor went to this resistor, its source resistance. And then that resistance went to this input. And then input here goes to ground. Let's see. Change the value of this capacitor here. We're going to right click on the C and we're going to make it, I can't remember what it was. I'm going to say 10 microfarads. Okay. This resistor, I believe it was 1.1K. And then we have this, we're going to right click on this source right here. We don't want it to be DC anymore. We want it to be a sine wave. So I'm going to click on advanced and it brings up this window. And I want it to be a sine wave, so I'm going to select sine wave here. I don't care about DC offset right now, and I can't remember what it was in the book. Hold on, let's see. I have it right here with me. Never mind. I will make this 20 millivolts. We can change it later. For the amplitude and for the frequency, I'm going to make it 10 kilohertz. And the rest of these we can leave blank as far as delay and theta. We can talk about some of those later, but we don't really need them. And then you can actually set the number of cycles you want this thing to run. Here, I'm going to leave it blank for now. So let's see what happens. So here is your sine wave. We'll talk about these others later when we get there. Okay. So now let's do simulation. You can't find it. Okay, cancel. So what's wrong? Ah, right here. I didn't tell it what the value of the capacitor, this capacitor was, so it complained. That should be, we're gonna make that 10 micro also. Okay. Oh, I forgot. We also have one more capacitor across here. So let's copy this one. Control R. And wire it up. But if I remember correct, this was 100 microfarads. I'm sorry, there's a question.
Would moving that ground under the right resistor change anything for the values to the RE? I mean,
I'm sorry, Mr. Ask the question again.
would moving the ground under the emitter resistor change any values for it? For the
No.
okay.
No, all it sees all this is just one wire. So if I right click on this, I say highlight net, it just sees it as a wire. It doesn't matter where this ground symbol actually is anywhere along this wire. And oh, there's one more thing I want to add. We have a new label node here, and this is actually VN. And I'll label, oops, drop it here. And this neighbor right here, we'll call it VS for the source. And so now all of these nodes should be labeled. So when I run the simulation, I should be able to click on either one of them and pop it up on the in the plot window, and I'll be able to know which waveform I'm looking at. So let's do a simulation. Run. That's operating point. Oh, I missed something. Still on the operating point. Simulate. Command. No, edit. Simulation command. I need to come here to transient because we're going to run it as a function of time. And see, let's run it for, see, what was it? I said it was 20. Oh, 10K. So that's 100 microseconds. So let's do, I don't know, 0.5 milliseconds, 500 microseconds. And here in the window, you can, let's say I was running a long simulation and I didn't want to bog my computer down with a lot of data I wasn't interested in. I could tell it when to start actually saving data. It'll run the simulation and not save any of it up until some time point, and then it'll start saving the data for me. And time step, I mean, it's calculating these points in time. And right now the time step is set in one of those previous windows. But we can change what the maximum time step is. Sometimes you want to make the time step small, because if you don't, then you may get an output waveform that looks all jagged. But we'll look at that later also. Anyway, that's so now you get operating point and it runs a transient. And now if we were to run, let's close this. And what we have is our schematic. And then we also have a simulation window up here, which shows us absolutely nothing because we haven't told it what to plot yet.
Sir, so when we were setting up for transient, what did we put in all those boxes? I know we put like 1.5 for the time, but what did we put for the other rest of it?
We didn't do anything for the others.
So wait, how?
Hold on. Let's go back. Hold on. Trying to get back to the window now. Okay, well, let's kill this and let's go back. Simulate. Edit simulation command. When I go to transient, all I tell it was run it up to a half of a millisecond. That's it. It'll use default value for all the rest of them, which are set elsewhere, but we don't have to set those right now. Is that the question you're asking?
Yeah, but I'm trying to get mine up. Wait 1 second. I'm trying to see if the okay, so let's run through that again. So when that box came up, all you had was 0.5, and then after you clicked OK, that little screen at the top came up, correct?
No, not yet. Well, the screen at the top comes up when I tell it to simulate to actually run. All I was doing then was telling it to put in this extra command here to actually run a transient simulation. So it's still running the operating point. And then when it's done with that, it automatically runs this transient. And that's when it pops up that little window, a plot window. So let me do it. Here we go. Run. So it's running the simulation. It's saved the data. I haven't told it what to plot yet.
So mine won't do that. So after I had changed to transient and I click run, it gives me an error.
What does the error say?
It's Ltspice netlist error declaration instant name. Wait 1 second.
Hold on 1 second. You're running Ltspice?
No, Ltspice.
Okay. Did you run your operating point okay?
Yes, sir.
Okay. Did you draw in the rest of the stuff here?
Yes, sir.
Check to make sure they're all connected.
Okay. LT trying to see LTRT.
Let me close this out and I'll go back and we can look at a couple of things. And so we added this other stuff in. Well, okay, well, let's do it this way. Let's get rid of this transient and run your operating point only. Don't run the transient. So go to your simulate command window. Oops, wrong one. I have to simulate, edit command, and just delete this. So we're going to delete this transient part. Okay. And then we're going to do a run. Hold on.
Okay.
And so now it should also should give me the same DC values that it gave me before. So it has more nodes now. Say for example, here's my VC.
Okay, I found out what was wrong with it.
Okay.
So I had 2 resistors named the same thing.
In 2 different places.
Mm-hmm.
Okay, yeah. Because they'll think that those that'll do it. Okay, so now let me go back to edit simulation, do my transient, and say I will stop at 0.5 milli. Okay, and simulate. So now what I'm going to do here is I'm going to select nodes I want to see plotted. Can you see my screen here? You see a little probe that shows up?
Yes, sir.
Oh, I'm gonna go over here and I'm gonna click on the output, which is RL. Click on that node, and there's your output. But what does the input look like? Well, let's go over here and on the end and select there. And where did the end go? It just looks flat, right? Can you see my screen?
Yes, sir.
Why is VN so flat and V out so large? It's sort of a trick question. So if I come up here to this window, you see the little hand. I'm gonna select that. Oops. Oh, that's a cursor. I don't want to do a cursor yet. Actually, I'll come up here with my right click and select and delete this trace. Hold on, how do I zoom in? 1 second. There we go. You see up top here where I have zoom to triangle? These are magnifying glasses. I can zoom in on a section of this waveform. So I clicked it, bring my magnifying glass down. This is my actual input. So it's not flat. It's only 20 millivolts peak. And so we have actually a fair amount of gain. So you can see this goes from 0 to 10 millivolts, and this goes down to about minus 10 millivolts. So this is my input signal here. It's only, well, I put in 20 millivolts peak, but my output is much larger. So we have a lot of gain here. And so if I take the ratio of this to this, that will actually be the gain of this circuit. Now, something I've done by accident earlier, you can go ahead and do it intentionally now. For V out, I put this little hand here, left click, and it brings up cursors. So I can pick out, let's see, find my cursor, how to get my cursors to move. So I come over here and I click on this top part right here, and it tells me that the vertical value is, hold on, I'm looking at the wrong one. No, that's right, almost 20 millivolts at, oh, I'm sorry, I'm missing my, here's my cursor, I'm sorry. I need to eat something, it's been too long. Let's see if I can move my cursor, here it is. So I can actually move my cursor. And right now I'm measuring the peak value of the output at 1.4 volts. And then the negative peak of the output at about negative 2.1 volts. So we can put cursors in here and do the measurements for us. And it shows up down here in this window. And let's see. And you can also do a differential cursor. So I could look at the difference between 2 time points. Let's see. So I come in here and I click again, and now I have another set of cursors. So I have cursor 1 and cursor 2. So let's go here. I put cursor 2 at the bottom. And I'm going to put cursor 1 at the top here. And what I have here is, here's cursor 1 values. Here's cursor 2 values. And here is the difference between the two.
How did you differentiate the cursors? What did you click again?
Well, it just generates the different. Once I put in the cursor 1 and cursor 2, it automatically generates this differential here. But to get the cursor 1 and cursor 2, I came up here with my little hand and I clicked on the waveform. It gave me one cursor. I click on it again, it gave me the second cursor, and it just automatically gives you this differential here.
Okay.
You don't have to do anything for the differential. So we'll see now that the peak output is about 3.5 volts, but our inputs, which is on this guy right here, is only about 20 millivolts. So we got a pretty nice amount of gain out of this circuit. But how do we, and we'll get into this later in class, but let me just tell you, you see this capacitor right here? This capacitor is responsible for this circuit having so much gain. If I wanted less gain, I would just take this capacitor out and the gain of this circuit would drop like a rock. But we'll look into the analysis in class about why it does what it does. And that, class, is all I want to cover on Ltspice simulation. So your assignment is to go back through the analysis we did in class last night with the circuit, build this circuit in Ltspice and simulate it, and I need a table. One showing the hand calculation, the other showing the simulation. That's lab 1. And to finish this off, hopefully next week, we'll actually go to the lab and build this circuit and do the measurements. And so we're going to compare all 3. Okay. Any questions or comments?
I have 2. We send this video out and we post the notes from the for
Yes.
this class.
Yes. Yeah, as I mentioned in the beginning, I had some technical difficulties last night with scanning for some reason. So I'll redo it and send it out tonight.
Okay, thank you.
And that is the quick and dirty version of Ltspice. It does a lot more cool things, and we'll get more and more into it. We're going to be using Ltspice throughout the rest of this term, in addition to building stuff in the lab. So we're going to do hand calculations, we're going to do simulations, and then we're going to build it and make sure. Because what the hand calculation does is get you in the ballpark, if you know what you're doing. What the simulation does is does the grunt work for you. The simulation should not be used in lieu of your understanding how something works. It's like, well, let's just simulate it. It's like, no. You should understand. You should be able to do a hand calculation. The simulation tool does all the grunt work for you, because we can run this over temperatures. We can change the supply voltage and see how this changes the gain of the circuit. And we can automate all of that. That is what the tool is for. It is not to think for you. And once you get your hand calculation looks okay and your simulation looks okay, then you can go build it and have some confidence that what you're building is actually going to work the way you intended for it to work. That's the process for designing electronics. Actually, that's the process of designing anything. Electronics just happens to be the class in which we're doing this in. Okay. Ltspice, I mean, you can also use this for digital logic. I mean, we're going to be focusing on analog circuits, but you can also use it for digital circuits also. Okay. Any other questions or comments? I will redo the scan of the material and send it to you. And actually, if you want, I'll actually send you the video of this, which I'm recording right now. Okay. But there are also other tutorials out there on YouTube for doing Ltspice, so feel free to take a look at those if those are helpful for you. Okay. And that is all I have for tonight. So send me an email or text me if you have any issues, and I'll get this I'll get these notes to you before 9 o'clock. I'm gonna sit here and try to see can I get them to scan again. Well, they scanned for some reason. I don't know where my tool actually put the file. I couldn't find it after you scanned it all in. Let's see.
Yeah.
I'll stop.
See you next week, sir.
All right. Everybody have a good week and a good weekend, and I'll talk to you later.
Okay, you too.
All right.